Any doubts on that? Sure. So we said insert will work the same way as search. It will work the same way as search, but wherever you are supposed to find that node and you find a null, you insert that. Okay. So suppose you were searching for 78. What will you do? You will keep on going down from 13 right, 21 right, 89 left, 55 right, and there is nil. So that means you have to insert 78 as a right child of it. So this is the logic is very easy. So yeah, you can write the pseudocode very easily. So we have to do insert xk, and k is the key that you want to insert. So if k is less than key of x, if the value of k that you're searching that you want to insert is less than the key of x, uh, where would you go, left or right?
Sir, left.
Then you will go left. So there, if so, this would be okay if this is null. So if left of x is null or nil, whatever you're calling, yeah, I can even do it in the beginning itself. Right? I can modify that. We can say no, I think that would create some trouble. So yeah, if key of x is less than k, right? So that means, oh, I was talking about a condition is greater than k, right? Key is greater than k, I have to go left. So then I will say if left of x is equal to nil, at that point, I have to insert a new node as a left child of x. So we have to say add k as a left child of x. Okay. Else, else means yes, left x is not nil, so you will continue your search. So you can recursively call this insert function. So else you will say insert left of x, this value k. Right, and similarly there will be an else corresponding to this if. This else will talk about, okay, if key is x for less than k, you will do things for the right of the right of x. So you will have a very similar function. So this is how the pseudocode will look like. Now what does it mean? What will you do here? When I say add k as a left child of x, what are the things you will need to do?
So change address stored in left x.
Right? So left x is currently pointing to nil. Yes. So that means I have to first create a new node using malloc. I have to create a new node. Okay, and make sure that the left pointer of x points to this node, right? So left of x, suppose this is y, becomes y, right? And it's oh, can't you see my screen?
So we can.
We can see it.
So we create a new node and then we y. Sure. And left x is y, right? And what we have to do, we have to make sure that the parent of y becomes x. So parent of y becomes x. And when we create a new node, we automatically create its left and right pointers as well, okay, by default. So when we create a new node y, that means it's left of y and right of y, and both are null. And this will create your node, and this will also create all the required pointers.
The key of y should be equal to k.
Right, yeah, good. So when we create, we also have to define the key. So what is key of y? That will be key. Yeah. Good. So three things we are doing: key, left, and right. Yeah, some of you were asking we should tell you some C codes. So today in the tutorial, we will. Not muted. Can someone tell me who is not muted? I don't even.
Anymore. It's not really my style of video. I'm more of like I like have like a impulsive idea.
Okay, so yeah. So yesterday you were saying to actually show you certain codes. So we will do that today. So that is how do you define a new node in C and how do you do some basic operations. And even the question you were asking, how do you take a binary tree as input? Okay? So we will do that today in the tutorial session. So here I just gave you the basic that, yeah, this is all you will need to take care when you are saying, oh, add k as the left child of x. This all will go. So this is how your insert will look like. So insert is quite easy. Complexity, same as search, right? Search. Complexity will be order h. So fine.
Sir,
Yes.
sir, suppose we want to write this insert function, but without any recursive call.
Yeah, you can do
Sir,
that.
sir, how, sir?
You have to use while. You can always convert a recursion into iteration. So you have to use a while for that.
Okay, sir.
You have to keep on going, right? And instead of calling this insert, you will have this while loop. While this is not null, you will keep on. So actually all of these codes, the delete, insert, you can search, you can write as both recursive codes and iterative codes. Some might prefer iterative code than the recursive codes.
Sir, here if k is greater than kx, then all the left will become right, right?
Yeah,
Yes.
that's all. Yeah, just replace left with right. So this was about insert. Now let's talk about the third main operation, that is the delete. So how do you DST, how do you delete a node? What is so special about delete? Yes, I can delete a node. So, but where I have to see where the node is. What is the property of that?
Sir,
So, yes.
sir, I have a doubt in means in the insert part when the element would be the greatest element.
So what?
So, sir, how, means we will put this left right of x as y, no, sir, or this definition would be remain same for like creating the node part.
No, this is for this particular thing, right? When it was in the left, you're creating a left child.
Okay,
If you're creating a right child, will
okay,
change. It will change.
okay, sir. Sorry.
Now let's talk about deleting a node. Okay. Let me actually give you a binary search tree, and then we will see from. So suppose this is my tree. Let me just.
Sir,
Oh,
335
sorry.
and 325
Yeah.
cannot.
While copying, I made this mistake. It should come. Yeah, good that you were verifying. We would have found a mistake while there was some problem with the algorithm. Okay, good. So yes, this is a binary search tree, right? No problem here. Now let's try to delete some nodes. So let's say I delete 10. Let me delete 10. What can you do to delete 10? What do you need to do if you want to delete 10?
Sir, we just erase the address stored in pointer left of circle.
That's all, right? So that means, so delete 10 is very easy. I delete it. And what I need to do, I need to uh, put its left pointer as null. This will become the left pointer. That's all. You have to see whether it is a left child or right child of its parent, and accordingly that pointer you will create. Similarly, suppose you want to delete this 400. So 400 you can just delete, and you can say, okay, the right child of 350 is null, and you can delete 400. So that means what is so special about 10 and 400 cases?
They are
Leaf nodes. So suppose I want to delete a node X. Okay. Or let me use some others. Let me say I want to delete a node Y. Okay. So if Y is a leaf node, then just remove it. And what does that mean? Modify the parent to replace this with nil as its corresponding child. That's all. So if it's a leaf node, very easy. Fine. Let's go to slightly higher complexity. What if it has only one child left or right? Is there any node in the tree that has only one child?
Sir, 75.
Now we have got, but earlier it was in full binary tree as per our definition. There's no node that has one child, either 0 or 2. So now we have got one node 75. So let me just remove it. So let's say we can just say okay, fine. Let's assume this is removed. Now 75 is a node that has only one child. So if I want to delete 75, suppose I want to delete 75. Delete 75. So what do I need to do if I want to delete 75? What can I do?
Sir, we need to link the 90 to the left of 100.
Right. So that means if y has only one child, if y has only one child, what we will do? So we will elevate that child to take y's position. That's all in that. So that means 90 will come in place of 75. So what do I need to do for that? So if I have to put 90 in place of 70. So you see in the general case, instead of 90, there could have been a whole subtree. There could have been a whole subtree rooted at 75. Doesn't matter. So there will be a root of that subtree. So what will I do? I'll take the left pointer of y's parent. So I have this y. I take its parent. This is the parent of y. I'll see whether y is the left or right child, and that pointer will now go to this pointer, will relocate to this node. Okay. So whether y was left or right child, accordingly that pointer will relocate to this node. Okay.
Sir, what would be the difference if, hello sir,
What will be the difference?
what would be the difference if the means the only is at left or right? You are saying that we have to check whether it is left or right.
No, which one are you saying? Y's child or
Means 9, for example, 90 is the left right child of 75.
yes?
And if there's a possibility that one of the numbers is left child of 75, so what would be the difference between them to add it to 100?
No, your question is not clear. See, we're talking about a case when I have to delete a node that has only one child.
Yes, sir.
Okay, so 75 here has only one child, that is 90. And I'm saying in general case, 90 can be a subtree. Whole subtree. May not be a singleton node, can be a subtree. Okay?
Yes, sir.
Doesn't matter, that doesn't matter. Now tell me, what is your problem?
So, like if 90 is right or left or right, it doesn't matter to add it to 100, right, sir?
It doesn't matter. True, doesn't matter.
Okay, sir. Yes, sir.
It
Yes, sir.
should
That
not
was
matter.
my doubt. I thought
Because,
it matters.
yeah, it doesn't matter because all these things are less than 100. Less than 100. So if I remove this and put this, that is also less than 100. If I remove this and put, suppose 10 was the child, then also it's less than 100. It doesn't matter. So whatever it is, I will put it. So I'll elevate that child to take y's position in that tree. Okay, and then I was just explaining what in the program what you will have to do. You have to actually check, okay, who was y's parent, and what was the actual pointer that was pointing to y? Was it left or right? If it was left pointer, you will have to relocate that pointer to the child of y. Okay, so this is the main change. Second change is, what is the second change I will have to do? This is one change I will need to do. What is the second change?
Or change parent
Pointer
of
of parent.
Parent of 90. Yeah. So parent of 90, was pointing to 75, and that will relocate to the parent of node. So these are two changes. And 75 is now cut off from the, will be cut off from the tree, and you can free or whatever. So this is how you can do this. Delete for a node that has only one child. So you have to modify y's parent and parent pointer of child.
Sir,
Yes,
the parent of 90 should be changed to parent of 75, right?
yes.
Okay, sir.
Okay, so deletion of a node that has one child is fine. Okay. Now let's take the third case. If y has two children, that is the last case. Cannot more than two children not allowed here. Okay, in a binary tree, only two children at most. So now, what will I do if y has two children? So let's take a node 300. So let's take 300 as my y. So delete 300. What will I do then? If you have to delete 300.
So maximum element of left subtree or minimum element of right subtree will be replaced there.
So you see what will happen if you delete 300. You see it's not so straightforward because, okay, I have to take care of both the subtrees. There can be a subtree here. There can be a subtree here. And the BST property should be maintained. So in general, so you have to delete a node that has a left and a right subtree. Okay, so I have to delete this. So if I delete it, look, so what will happen now? The tree will become disconnected. You will get two subtrees and you do not know what to do. But there you can actually use some idea. Idea is that, okay, all these values are less than y, all these are greater than y, and this is y. So to maintain the BST property again, what will you have to do? So suppose you find just the successor of y. So suppose you find successor of y. Where will that be? Where will you find the successor of y?
Right.
The leftmost element, the keep on going left. So you keep on going left in the right subtree, and you will find a node that is the successor of y. The minimum value here. So this is the successor of y. Okay. So what if you delete that node and put in the position of y? So now you delete this node and change the key of y. So suppose this node is z, and change the key of y to be key of z. So something like key of y becomes key of this node z. And then you delete this node. And then you delete this node. Will that work?
Sir, does that mean we are deleting Z and replacing Y?
No, what you are doing, you are changing the key of y with the key of z. Okay, you will just say, okay, what is the key of z? You put it here without modifying any pointers or anything. But you delete this node.
Z.
delete this chat.
Okay, sir.
Okay, you delete chat. So this is the first thing you will do. Second, delete this node Z. Now the question is, oh, looks like recursion now, right? So I'm talking about deletion and I'm saying to delete a node that has two child, I have to find its successor node and I have to delete that one. So what if that node has two child again? So what if Z has two children again?
Sir, how is that possible?
Sir, in that case, Z will not be. Yes, sir.
Please.
I just wanted to check that. Okay, good. So you are saying Z cannot have two children. Anybody who cannot see this? So the point is Z can't have two children. Why?
Because if it has left children, then that will be the successor of Y.
Because I have to keep on going left, right? So what I know is that Z can't have a left child. If it has left child, it cannot be a successor. Then you will keep on going there. Right? Z cannot have a left child by definition. So that means it can have at most one child. Then you can go back to your one of your earlier cases. So that means,
Excuse me, sir. I have a doubt.
yes.
Yes, sir. Here we are doing the we are putting the key of Z at the place of Y. So, sir, will it be a cycle then if we are putting the pointer to the Z at the place of the pointer to the Y? Then
No,
it
no, no, no,
will
no,
make
no,
a
no.
cycle.
What cycle? No cycles there. It's a binary tree, not a graph. No cycles. Okay, let's see what
Yeah,
cycle
but
is.
sir, at the place of key Y, we are putting the pointer Z, and then
Not
it will
pointer, not
write.
pointer, key of Z. I'm not putting a pointer. I'm just finding out the key of Z and putting in place of key of Y. Okay?
But at the time, we have to delete the Z, the key of Z,
Then you delete Z.
which is.
Delete Z the way you were doing other deletions. Then you have
Okay, sir.
nothing to do with Y. When you're deleting Z, you have nothing to do with Y. You forget about Y then.
Yes.
Okay?
Okay, sir. Okay. Yes, understood.
So go back to one of the earlier cases. Fine. So now let's go back here. If I delete 300, what will I have to do? Here, delete 300 means find successor of 300. What is that? So you take the right subtree and find the leftmost element. That is 325. So 325 is the successor of 300. So that is 325. Okay, now you put the key as 325 here. So this will become 325. And then you delete 325. And then you delete 325.
Sir, we can go left and
Of
then we
course.
can get
Good. So yeah. So you are saying there's another option. We can also do the same thing by finding predecessor of one. We can do the same thing by finding predecessor of y. So I can say what is the predecessor of y? In this case, it's just 250. And yeah, I put the key as 250 and delete that. So, okay, so we are done. Any other case that can happen in delete?
Sir,
Sir,
Yes.
can't we do like replace the Y with the right subtree and replace the means put the left subtree at the bottom of the right subtree?
So are you saying something?
No, I'm just thinking what he said. So he said that instead of y, I put that pointer as the right subtree, okay, and the left subtree I move from there and put at the bottom. Bottom, you mean the leftmost child?
Yes, sir.
Sir, apart from successor and predecessor, any of the leaf will work, sir.
So that will not work because then 250 will not be greater than means.
Will not be greater than what?
No, sir, it is working. It is working.
Seems possible. So what you are saying, yes. So let's see in terms of properties. So you have the situation y, left of y, right of y, that are less than y and greater than y. And what you are saying, fine, I can put this whole left subtree, this whole thing here. That shouldn't be a problem because these values are less than y and these are all greater than y. And you put all these things here. Sure, that should be fine. And then once you do that, then it is like as if you're deleting y with a single child. So then, yeah, you can elevate it here. Yeah, I mean that is a possibility. You can do that. I don't know whether that will take maybe I don't know whether that will take less time or that looks like similar complexity. Looks like similar complexity. You have to still find that leftmost thing here and put the pointer. And then you delete y like your normal case. Yeah, possible. I don't see any problem.
So can you explain? So we can make other leaves also.
We can make.
So if we go right and then the left, then any leaf of that subtree will be replaced. Can be replaced with y. Or first left, then right.
So what are you saying?
Like sir, if we go from 300, then 350, and then from 350 we go to 335. Then any of 355 and 340. We can replace any one of them with 300.
How?
No, sir.
How can I get 300 there? This will not satisfy the BST property.
What are you saying, sir?
No, you were saying after 335 you can go either left or right. Or 325 you are saying, 325.
Yeah, 325.
That's what I think you said. 325 once you
we
reach
can do it 340 also. 340 also.
How you can do it 340? 340 at this point, all the nodes here should be larger than 335. So at 340, if you put something that will, I do 300, this will not satisfy BST. You can go only to the predecessor and do something. I mean, you can only go to the successor and do something to ensure the BST property. You see, this is what is happening. Less than y, y greater than y. So you have to do whatever you can, you are doing, keeping that in mind. Yes. So if you find the successor of y, you know that, okay, you can put the left child, that values, all the values there, all of these values can be put as the left child of this. No problem. Okay? Because they are less than y, and the successor will be larger than y. So left subtree can accommodate all the values less than y. But you cannot do it arbitrarily on any. That is not possible.
Sir,
Yes.
sir, but for a given set of data, a binary search tree should be unique, right?
No, who said that?
Sir, I mean it is like sorted, so there
No,
is
what
a
do you mean binary search tree is unique? When the input in the order in which you have to put the nodes is given, it is unique. But for a set, it is not unique.
okay, sir.
For a set of data points, the binary search tree is not unique. We talked about it yesterday, right? 1, 2, 3, 4, 5. You can have so many binary search trees. You can have 3, 5, 4, 1, 2. I mean, so many binary search trees you can have. So why are you saying this is a unique thing for a given data? But if you fix what is the order in which they are coming, and you have to insert in that order, yes, it is unique. It is unique. Okay, any other question on binary search tree? I'm happy that, yeah, we found another method. So, but yeah, that's good. So you can, important is remember the binary search tree properties, and then you can play. Then you can play with your algorithms. Okay. Anything else on binary search tree delete? So we talked about search, insert, delete. All of these take order as 10. Now, where were we all stuck in the beginning yesterday? We were saying, oh, good, order H, but H is order N. H is order N. Now, and then you were saying, oh, then what is the use of binary search tree? I can use an array, sorted array, and binary search. So here, these all will go to order N. All this complexity will go to order N in the worst case. And a sorted array is better. Right? There also, there in search, in sorted array will become order log N. And other things can become order N. This can also become order N, or 1 if you have to, if you want to just keep it, do not modify your array. But this will not be worse than binary search tree. So then what did I say? Why are we reading this?
There are some tricks to make H order log n.
Yes.
Sir, you said that there are some tricks to make H order log n.
Good. So there are some tricks by which I can ensure H is order log n. Some tricks. Haha. What are those tricks? What are those tricks? So what I need to do, I need to ensure, so if I can keep the height of a tree with n nodes limited to order log n, all these operations will run in order log n. Fine. So that is the thing. So now, how do I ensure that? How do I ensure that? And the idea is very simple. The idea is very simple. So here, what you will do? Yes, tell me.
Sir, if the numbers are sorted, then we will start with the middlemost element, then we will get
The root of the tree is in median.
No, that's all right. That's all right.
The
That's
tree
all right.
must be,
Uh-huh.
sir, almost complete or complete. Then we can do it like this.
No, but how do you ensure when you are inserting elements? How do you ensure that the tree remains? See, I understand what you were saying. You were saying, okay, if I have a sorted array, I can use some trick to have a balanced tree balanced. But what if I delete things? Right, I can play. I can also play. I can adversary can say, oh, I will delete some nodes, and then it will not be balanced anymore. Yes, after you create that tree. So you have to think in totality that maybe you created a tree that was balanced, but after some time somebody deleted some nodes, and then it is no more balanced. How do you ensure that it remains balanced all the time? Right. So that's where. So what now? Once you think about it, then the trick is easy. The trick is I have to modify the insert and delete in such a way that the height of the tree at any time doesn't deviate too much from the O log. So I have to modify them in some way. So that at every point I have some check to ensure, okay, is it deviating from order log n? If so, I do something and maintain that property again without waiting for it to become order n. Okay. So that means you have to do something extra. Do something extra. But the idea is that do something extra should also be within order log n. So that should be efficient. Should be efficient and should be doable in order log n time. Because if the extra thing takes order n time, then there is no point. Doable in order log n time. So that is what we need to come up with. What is that trick I can do so that at every point I can maintain that property? That looks very interesting. If I can do that, then yes, oh good. Then binary search tree, yes. Insert, delete, search, all in order log n. What is that? So actually, so there are the families where you put more constraints. So you went from binary tree to binary search tree by putting some more constraint. Now you have to go to a more deep. So you have to go to some families. They are called height balanced binary search trees. They will take care of this thing. Okay, and they have various tricks of doing that. So there are actually quite a few families. There are two that are quite popular. One is AVL trees, and second is red black trees. Okay, and in this course we generally cover AVL. Sometimes we do red blacks, but this time we are doing AVL trees. So what are the AVL trees? So they are binary search trees, but they will have an extra constraint so that they can ensure height to be order log n. So what is that? So let's inherit BST. So AVL trees are binary search trees with the additional property and what is that? For any node, the height of its left subtree. So they say, okay, I have a node, I have a left subtree, right subtree. The height of the left subtree cannot differ by more than 1 from the height of the right subtree. So any binary search tree that follows that property all the time is an AVL tree. That the height of the right subtree and the left subtree differ at most by 1. And if you can follow that, then you can show that height is order log n. And this is something you don't have to take my words. We will actually show that height actually remains order log n. So now let's try to understand how by following this property height remains order log n, and second, how do you ensure this property while you are doing all these insert, delete, etc. How do you ensure that this happens? Okay. So let me first give you the basic notations for the so let's formally define this property. So see, this happens for any node. Okay, so that is something interesting. In binary search tree also we define property that is true for every node. For any node this happens. Similarly here for any node this should happen. So formally, let U be a node in an AVL tree, and let L and R be the left and right subtrees of U. So then HL is the height of left subtree, HR is the height of right subtree, and what's the defining property? It says that HL minus HR, the mod should be less than or equal to 1. For any node, this should happen. Okay, and if we can maintain this property, height will become order log. So, question is, how do we maintain this property?
So it is like taking half on both sides effectively.
It is like taking
half of the nodes on left side and half of the nodes on right side. Means floor and ceiling type of thing.
That's okay, but yeah, means when you create a tree, you keep on doing insert delete. How you will maintain this property? Right? Isn't that interesting? You can do in the beginning. You can do right? In the beginning. You can create a tree with this property, but how do you keep on ensuring that while you do any number of inserts, any number of deletes? Okay. So yeah. First of all, let me tell what will change in the notation. I mean, in what is the extra you have to store? So what you have to do, so in addition to the left, right, parent, these pointers and key, you have to store something extra that talks about what is the balance of that node. Okay, a node in an AVL tree should maintain the balance factor. So this can be a simple integer like b, and it can take value 0, +1, -1. So these are permissible values. But yeah, I mean, when this will go beyond this, it can take values like 2, but it will not take values more than 2. We will see how. And this we will define. I mean, this is just a definition. This will be HR minus HL. We will take HR minus HL, HP. And this 0, +1, -1 permissible. And if it takes +2, -2, that means, oh, alarm. There's an alarm. Yeah, something has to be done. Something has to be done to ensure this comes back to +1, -1. Okay. So this is all. I mean, this is all they need to take care. And now this whole nice algorithm on how do you do it. First of all, yeah, let me just show you how we will actually draw an AVL tree. So each node, suppose this is your node, you will have a balance factor. And balance factor we will draw using like a scale. Okay, so you say if it is pointing up, that is 0. If it is, so we draw 3. If it is pointing here, that is -1. If it is pointing here, this is +1. Balance factor. Okay, 0, +1, -1. What does it mean? It is 0 if the height of the left and right subtree are same. So here you have the left subtree and the right subtree, and they have the same height. Let's say h. So that means this is your L, this is your R. So h of R minus h of L is 0. Here what will happen? Which tree will be longer? Which tree will have more height in this case? HR minus HL is -1. So which tree is having more height?
Left.
HL.
HL.
Left.
If this is H, this will be H plus 1. So here HR minus HL is minus 1. And analogously, what will happen here? The L will be of height H, and the R will be of height H plus 1. So that means HR minus HL is plus 1. Okay, that is how we will draw AVL trees. We will show the balance factor. We will have left and right subtrees with their heights. Okay. Now, I have a question. Okay, yeah, I'll come to that question maybe in a bit. So now I want to prove, let's say I want to prove that an AVL tree following this property will ensure that height is order log n. How do I ensure that? How do I prove that? That, okay, by following this property, height will remain bounded by log n. H is already omega log n. We saw that. But how does that ensure H is order log n? So we have to prove this. Okay. So how do we prove it? So let's say I'm given an AVL tree of height H. So I want to prove it by saying, okay, see, when will this height be maximum? When the tree has minimum number of nodes, right? So height is fixed, and this, if I can find out what is the minimum number of nodes that tree can have, maximum I know, but what is the minimum number of nodes this can have? So what is the minimum number of nodes? It can have. Suppose this was not AVL, BST. What is the minimum number of nodes? If it was in simple BST?
H plus 1.
H plus 1.
H plus 1.
But if it is in AVL, what is the minimum number of nodes? So we will try to prove that, some bound on that. So let's say, let MH be the minimum number of nodes. Okay. Now, can I get a relation for MH? Can I get some sort of equation for MH? So overall I know, okay, I have an AVL tree that has a height of H. So it has a left subtree, it has a right subtree. What are the possibilities? Let's write down the possibilities. One possibility is left is height H minus 1, right is height H minus 1. Case 1. Second is left is height H minus 2, right is height H minus 1. Case 2. And third is H minus 1, H minus 2. Any other possibility? Any other possibility?
No, sir.
Yeah. Okay. Now, which of these possibility? So now for MS to be minimum, I mean, for the number of nodes in the AVL tree to be minimum, for MS to be minimum, L and R should also have the minimum number of nodes. Also have the minimum possible nodes for their corresponding heights. Because if they don't, I can remove a node, and there should still be a tree, and that is then my original claim is not correct. So for their corresponding trees. So now, which of these three possibility I can ignore? So which possibility?
The first possibility.
Case 1 can be ignored. So friend is saying case 1 can be ignored. Anybody disagrees with that?
Sir, why we are discarding the possibilities?
You see, there are three possibilities, right? But what we are saying, I want to find out what is the minimum number of nodes in an AVL tree of height h. There are three possibilities. For it to have the minimum number of nodes, its corresponding left and right should also have minimum number of nodes, minimum possible nodes, right? If they don't have, I can, huh?
Their sum should be minimum.
If there are some,
There, the sum of the nodes in left and the sum of the nodes in right, this should be minimum.
right? So that means the individuals they should be minimum. Otherwise, how will that be possible?
But sir, they are a branch of a tree, so they are interdependent.
No, they are not interdependent. Left and right are not interdependent. So what we are saying is that I have an overall tree. This has a left subtree, this is a right subtree. In AVL, I only care about the height. I only care about the height. Right? So its overall height is h. And what I'm saying, if they are both h minus 1, or one of them is h minus 2, another is h minus 1. So first of all, do you agree that for the overall tree to have the minimum height, I can ignore case 1?
Okay, yes, sir.
Because you see, if it was case 1, I can remove a node from L and R and get a lower, get one of the subtree of lower height. I can say, okay, remove some nodes to get h minus 2 height. This will still be an AVL tree. Remove some nodes to get h minus 2 height. And that means I am contradicting myself. I'm saying my tree has the minimum number of nodes. So this case is gone. This case is gone. So now both cases are symmetric. I can take any of this. Okay. So then that means one of them has h minus 1, another has h minus 2. Okay. Now what I'm saying, individually, they should have the minimum number of nodes. They should have the minimum number of nodes also. Minimum possible nodes for their corresponding height. Because if they don't, I can replace this with another tree that has less number of nodes of the same height. Does that make sense? Yes, no?
Yes, sir.
Okay. So then can I write it? Yes.
Sir, for AVL tree means this property of HR minus HL should hold at each and every node, right?
Yes, each and every node.
Okay, sir.
That is the thing, not only at the root. Because you see, otherwise what can you do? You can have a root, you can have a full, complete tree of height, and then you can have a like this. And you see, it will not be balanced. It will not be balanced. So, yeah. Or whatever, you can have, in the worst case, you can have, both has like this. Like this. That is better. So property is holding, but it's not balanced. So this should happen for all the nodes. So then once you are clear that they should also have minimum possible nodes, can I write an equation?
Yes, sir.
Yes,
What
sir.
is it? MH?
MH equals 1 plus NH minus 1 plus
Mhm.
NH minus 2.
Oh, that starts resembling something. What does that resemble?
Set Fibonacci series.
Right? Just one thing. There's a plus one here. So how can you take it to Fibonacci? What trick you can use to convert that to Fibonacci? Okay, let's find the base cases. What is M0? What is M0?
1.
1. What is a tree of height 0? Singleton node. Okay. And what is M1?
2.
right? Now here I have a question. For this particular node, what is HL, what is HR? For this node, what is HL, what is HR?
1 0.
What is the balance of this node?
So will
Minus
M0
H.
be 1 or it will be 0?
Huh?
M0. Will it be 1 or 0?
M0 is 1. M0 means a node of height 0. That is this one. Right?
Sir, what does M represent here?
M is the minimum number of nodes in an AVL tree of height H. That is MH.
Okay, sir.
Minimum number of nodes in an AVL tree of height H. Okay, so HL, what is HL? HL is 0.
Yes, sir.
What is HR?
-1.
Minus. Okay, this is just a convention we take while we are talking about AVL trees. In general, also this is fine that an empty tree has a height -1. So empty tree has a height -1. Okay, if there is a singleton node that has a height 0, so then it is okay. This HR is 0 -1, HL is 0, so HR minus HL gives me the balance vector. So M0 is 1, M1 is 2. Okay, that is the base case. Now, what is the trick to convert that to Fibonacci?
Add +1 to both sides.
Yeah, MH plus 1 is MH minus 1 plus 1 plus MH minus 2 plus 1, and let's say NH is MH plus 1, MH plus 1. Okay, so then I can say, okay, that is NH is NH minus 1 plus NH minus 2. And what is N0? N0 is M0 plus 1, that is 2, and N1 is M1 plus 1, that is 3. Okay, in terms of Fibonacci, what are these? This is F0, F1, F2, what is this? Or F3?
F3.
F3.
This is F3. So NH is F of H plus 3, right? So NH is nothing but F of H plus 3. So once you understand that, then can you say something? We know what is Fibonacci. This comes out to be 1 by root 5 rho to the power h. So this will be h plus 3. And then we can say that this n is greater than equal to number of nodes in the inequality will always be greater than equal to mh. That is 1 by root 5 rho of h plus 3. mh is nh minus 1 minus 1. Okay, and this will give you the connection that h is something like 1.44 log. From there you derive this.
Sir, can you explain F3?
Sorry?
Sir, can you explain what is F set and there what is rho? I didn't get it.
Do you know this connection that f Fibonacci series hth number I can write as 1 by root 5 rho to the power h? Do you know that?
No, sir.
Okay, then fine. So I think, sure. Anybody else knows that? Anybody knows that?
Sir, what is rho, by the way?
Rho is just a constant that okay, fine. So let's do this. So I think we should start your tutorial. I'll explain what is this thing. I think this thing is what is creating issue. I'll explain what is that, and from there we will again just quickly come back to this. Okay, so I'll do that in next Wednesday. Then next Wednesday I'll do that and complete this. The other interesting thing, how in insert and delete I ensure this property. So okay, so now what we will do, as you were all wanting, we will show you some codes that will help you for getting along with binary search trees. Okay, so Soumya, I think you are there.
Yes, sir, I'm here.
Are you already a presenter, or do I need to make you a presenter?
You need to make me, sir. I'm not a presenter right now.
Sure. Okay, Soumya, can you try now?
Yes, sir. I'll just. Yes, so I hope this is visible.
Yes, yes. Sure, Soumya, over to you. So for the class, so Soumya will start with showing you some very basic C codes and take this interaction time. You can ask your doubts, and then she will explain what was the last year's assignment. Okay, that was a bit more complicated. We will try to keep it simpler this time, but yeah, so you should, yeah, pay attention to this. And I'll continue with where I left on next Wednesday.
Okay. So we'll start off with some, as I said, we'll start off with some very basic code walkthroughs, and then I'll showcase the last year's assignment. And then these are just some small problems that you can practice for homework. So let's start with the basic node definition that is there. I'm sure all of you are aware how to define a node structure and how that would work. So let's say we define a struct node where you have the int data, where you will store your integer, and you have a pointer to the left and to the right, which themselves are node structures.
So here I have also told them that they can use parent pointer, so that will just go as another thing, struct node star parent. That's all. So that is optional.
Okay. Yeah, so over here you can have struct node star parent to have the parent pointer that sir has told. And again, at any point, if any of you have any doubt, then please just stop me. So to create a node, this is just creating a new node where you're assigning the data and you're assigning the left and the right pointers. And if you have a parent pointer, then you're assigning that as well. You start with creating the function definition, which is struct node star, which would be what you return from this function. New node is the name function, and int data is the parameter passed to it. Then you create a new node in this way, where you have struct node star temp, and here is you're assigning the data to that. You're assigning the memory allocation to that. Now, when you do temp data, you assign the input that you have data over here. And then similarly for the left and the right pointers, you can assign the null value right now because we don't know what the left or the right pointer might be. And we just return temp. Fairly simple. So now creating a binary tree. Let me put this here. Creating a binary tree. So let's assume that right now, you know the general way where you have a root node and then you insert to its left, you insert to its right. But let's consider the case where you have an array and now you need to create a binary tree using that. Okay, so over here, the array that you have is 12, 8, null. So what this means is you have 12 over here, 8 So the left pointer over here would be 8, the left child would be 8. Next you have null. So we assume that the right child over here, this would be null. Now 22 is the next input. So the last available node that you have, the left child to that, you put the value 22. Now again, the last available node, which is 8, because this still has not been filled, the right child to that, you fill the next value, which is null. So you fill null. Now you come to this point, 9. But over here, this was null, so we can't set any children to that. So you go to the next available node where the left or the right child has still not been filled, and you start with the left node. So you fill 9 over here, right side null. Now again you have another null. So again, what is the last available node for which the left or the right child has still not been filled? It's 9. So we go there. Now this says null, so which means we start by filling the left side first. So the left side we fill as null. And then for the next data value that we have from the array, we fill it as the right child. So we fill 12 over here. So basically when you have an array, you start with the root node and then you start filling first left, then right. And you do this for until every node, either your data is exhausted and every node, the left child or the right child has been filled. So let's look at the rules. Whenever new node is added to the binary tree, node is pushed into a queue. So now to do this, what do? You need a queue to maintain which is the last node where you can insert. So let's assume we have this queue. You insert 12 over here first, right? Now you know that the left child and the right child of 12 have still not been filled when you initially start making the tree. And the next value you have is 8. So you fill 8 over here, but do you remove 12 from the queue right now or do you let it be?
Let it be.
Right, because the right child has still not been filled. Then you go to the next value, which is null. Now we assign it to null and then we pop 12 from there. We dequeue it from the queue. Now we go to the next value that is there in the array, which is 12, and we pick up the first element we have in the queue, which is 8 right now. The value that we have is 22. So we assign it to the left child, which is this node. Put it in the queue and let 8 be because the right child still has not been filled. We go to the next value, which is null, assign it to the right child of 8, and then dequeue 8 from the queue because both left and right children have been filled. Similarly, you complete the entire array. So again, the rules are that whenever a new node is added to the binary tree, this node is pushed into the queue. So when we added 22 over here, we pushed it to the queue. A node will stay in the queue until both of its children are not filled. And once both the children are filled, the node is popped from the queue. And the steps are simple, that you create a queue, you start by creating a queue, create a node from the first array element and push it to the queue. One by one, you create a node from the next element in the array. And if the first element of the queue has a left child, you insert there, else you insert it as a right child. And once both children are filled, you pop it from the queue. Okay. So let's look at the code a little bit now. So let's say we have a function called insert, and the parameters of this function are that it takes in the root node, it takes in the data that you wish to insert right now, and it takes in the queue that you have been maintaining. So you create a temporary node with the data node, and then you check. So what would be the base case over here? The base case would be that there is no root right now, and the first thing that you're doing is creating the root. So in this if condition, yes, so in this if condition, we check if root exists or not. If it does not, then this is the first node that we've encountered and we set it as root. Else, what do? over here, I'm assuming that you have the queue structure and all of those functions created. So what do? We get the front of the queue, that is queue.peak, or written in this way, that you get the front of the queue. And now this depends on the implementation. So let's assume that we are putting null also in the queue. If that is not the case, then you don't need this. But you get the front of the queue, and then you check if the front does not have a left, then you insert the current node that you have as the left node, else you insert it as the right node. This is the else condition, and then you insert it as the right node. And if you have inserted it as the right node, that means both left and right children have been filled. So you dequeue this particular, so you dequeue the last element from the queue. And what you do is the current node that you had, the temporary node, you enqueue it. Does this make sense?
Ma'am, what does this first if condition means? Means not of star root.
So what this means is, you can also understand this as if root equal to null. So if root is null, then set root to be the temporary node.
Yes, ma'am.
Okay. Any other questions over here?
Can you please show an example where the tree is not a linear tree? I'm getting confused how the rules work.
Sure. Okay. All right. So let's take an example where we have 50. Over here we have 20. 60. Sorry, this would be 15, 30, 55, 70, and then let's take 80 over here. Okay. So now you have an array which represents this tree. Okay. So what would this array look like? It would look like 50, where you have the first element. Its left child, which is 20. Its right child, which is 60. The left child of 20, the right child, 55, 70. Now here comes the tricky part. If let's say I have 17 over here, then what I would have is null and then 17. Okay, because for 20, we've exhausted both its children, right? For 60, we've exhausted both its children. So now we have 15. For 15, the left child is null, the right child is 17. Then you have to fill 30 left child and right child. So you would have null and then null again. Similarly for 55, so you would have null and then null again. And then for 70, you need to fill the left child and the right child. So you would have null and then 80. Does this array representation make sense?
Null in an array.
It can be -1 if you want. It can be int max, int min. It can be either.
Ma'am, can you please
Yes, it's clear now.
Ma'am, can you please explain once again from the null, the 17, before 17?
From 17, okay. So what you have is your root node is 50, right? So when you're creating the array, you start by filling that. Your left child is 20. So when you start, let me pick a different pen here. Okay, so you have 50. Now your first element is 50. The left child of 50 is 20. So you fill that. The right child of 50 is 60. So you fill that, right? Then you start by filling, when you're doing this, when you're representing it in this way, this is also known as the level order traversal. Okay, so you have 50 over here, where you have the first level, and then you represent the second level, which is 20, 60. And then you have the the third level, which is 15, 30, 55, 70. So when you start with 15, now 50, it's children you've already filled, so you won't look at 50. Now you don't look at 50. For 20, it's children you still haven't filled. So you start with filling 15, 30, which would be the left child and the right child. Then now 20 has been filled, so you don't fill that. You start with filling left child and right child of 60. So 55 and 70, right? So these you fill, so let's not represent this anymore. Now you start with filling the left child of 15. Left child of 15 is null, so you have null over here. The right child of 15 is 17, so you fill that. Now you don't fill 15 because we've already filled this. 1 second.
Ma'am, what if there was no 30?
If there was no 30, then in place of 30 over here, you would have null.
So user will give null specifically instead of
Yes.
omitting.
Yes.
Okay.
Then, ma'am, in the next level, we don't add the two nulls.
Sorry?
Then when we write the next level, then do we still have to write null below 30?
No. Then in that case, we don't have to write null because a null cannot have any children, right? So we don't write any null over there. So
And
if
when
you remove
we have not
30,
defined
then
the children of 17 and 80.
17 and 80 we haven't filled, yes. So it's assumed that all of this beyond this is just null. Like everything which does not have any left or right children, then they're not going to have any children. So anything that has not been specifically mentioned, either way, it is null.
Okay.
Right? Okay, so now that you've understood this,
Input.
yes.
Ma'am, in this tree, all numbers which are greater are to the right, and all numbers which are less than, suppose, a node which is to the left. But in the previous slide, there was 8 and 23, and 23 was to the left of 8.
Right. So I've shown a binary search tree, but the same, if you look at the code that we have over here, and if you look at whatever I showed before, there's nothing specific that we've created for, we've not used the properties of a BST explicitly, right? Even if this was 5, instead of 50, I had 5. Instead of 20, I had 70. It doesn't matter because we've not used the properties of a BST explicitly over here. Right now, we are just creating a normal binary tree. So I've represented it in this way so that it's easier for you to understand, but that is not necessary.
Ma'am?
Yes.
So if we get a null, we do not push it into the queue, right? So that in
You
the
do not
next
push
level.
it.
Okay.
It depends. It's actually a design choice. If you want, you can push it into the queue, but it's better to not because it just adds extra steps. So which is why I said that this particular thing is not needed as such. The while part. Okay. Now is it clear? So given this array representation, you start with looping through this array representation, and you have a queue. So yeah, so you have a queue, and in the queue, you start by inserting the first element of the array after creating a node from that. So you insert the node 50, and then you go through this. So since you had no root in the starting, this 50 becomes your root node. Now, you end this you've enqueued it. You go to the next element of the array. You have data 20. You create a temporary node out of that. Now you look at the first element in the queue. It has no left children, so you put 20 as its left child. Then you go to the next and you put 20 in the queue. Then you look at the next element in the array, which is 60. You put that as the right child of 50. You dequeue 50, and then you add 60 to the queue. Does that make sense? Hello.
Ma'am, actually, screen is not visible. Yes, now it's visible.
Yeah. Yeah. So does the algorithm make sense and the way we've coded it?
Yes, ma'am.
Okay, great. So let's look at the next piece of code that we have. Now, what I'm doing is I'm assuming that you know how to create a binary search tree. If you don't, then I can go through that as well. Would you like me to go through a small snippet of inserting in a binary search tree?
Yes, ma'am.
Yes,
Okay.
ma'am.
Okay, let's go through that. 1 second. All right. Yeah. So for creating a binary search tree, if you have insert, okay. Now you have insert, which is the function, and you have the root node, and you have the data that you're trying to insert. Okay. So what do you check? If the root node is null, which is again your base case, then you create a new node using this data, and then you return that, right? Now in this function, we assume that we are always returning the root node. It returns the root node. Okay. And then this root node represents, and then this root node contains all the connections to the left child and the right child. Now you have, if there is no root node, if it is equal to null, then you create a new node using this data, and then you return that, right? But let's assume you have 50, which is your root node, and now you wanted to insert 20. So in this else condition, your x is smaller than 50, right? So it needs to be inserted to the left child. So what do? You do root left child, roots left child, and then you do a recursive function over here. So over here, we are inserting it recursively. And then you again call this function where in the first part, you return the root node. So over here, you return, you call a function on this node again. Now this node is null right now. So you return the new node, which contains the data 20. And then what will happen? When you recurse back to the previous step of the function, for 50's left child, the 20 node would be inserted over here. Did that make sense? How this would work recursively?
Yes, ma'am.
Okay. And then if you have the right child, let's say we are inserting 55 now. So you go to this else if part, you recurse on the right side. This right side is null right now. So you call insert root this. When you call this, this would be insert. Yeah, insert. And then you would have the pointer to the right child of the root, right? And then you would have, one second. Yeah, you would have the, okay, my internet seems a little slow, but I hope you understand that you would have the pointer to the right child of the root node, right child of 50. And then you again call this function with that. And since that is null, you return the new node, which would contain the value 55. And then that would be set as the right child of that. Right child of 50. Okay, does that make sense?
Yes, ma'am.
Let's see an example when you have a larger tree. So when you have, let's say 30 over 30 as the right child of 20. Give me 1 second. Let me try to adjust my Wi-Fi. Yes, okay. Let me share my screen again. Okay, I hope this is visible.
Yes, it's visible.
Okay, great. All right, so let's start with a larger tree where you have 50. Left child of 50 is 20. Right child of 20 is 30. Sorry, internet issues. Okay, but I'll try to speak through it and then you can try to note down in your notebook just to follow through. So the root is 50, the left child of 50 is 20, the right child of 20 is 30. And then now let's assume that we're trying to insert 35. Okay. So what do? You start with your initial call to the function, which is insert, and then you pass the root and your value is 35. So you check the if condition, if root is equal to null, but this is not the case over here. So you check if the data that you have, it is less than or greater than the root that you have right now. So 35 is less than 50. So you go to the else condition, this else condition, and then you call the function insert again. This is the recursive call that you have with the root as the left child. So the left child is 20. You call that again. Now the first call you made was with 50 and 35. The next call you're going to make of the function with 20 and 35. Now when you have the root node as 20, you check your conditions again. You check that 35 is greater than 20. So you recurse on the right side with the right child. So now the right child of 20 is 30. So again, you recursively call on this, and since it's larger than 30, then you, okay, let me try one more thing. Okay, let's try this. So your function calls look in this way. Your first function call will look like when this is the root node and this is the key. So you have 35 that you need to insert, 50. So you check your conditions, you go towards the left side, then you recursively call on 20. Your value for the value that you're inserting remains the same. Then you check your conditions again. You go to the else if part. Then you check that in the else if part, you recurse on the right subtree, right? So you go to 30 and then you recurse over here. Now you know that 35 is still greater than 30. So you recurse on the right pointer of 30 over here. Now this is null. So what do? You create a temporary node of 35 and you return it to the previous function. What does the previous function do? It sets the right child, that is this, as 35. So it does this, right? And then you just keep recursing back to the function and then you exit. Did this make sense? Okay. Now, if you're searching for a node in a BST, then again, you need to recurse left, right similarly, right? So you have the root and you have int x, and you have your base condition that either root is null, that you haven't been able to find it even after you've recursed as was needed, or that your data is equal to the root data. In that case, you return root, right? And your two conditions, either your data that you're searching is less than your root node, so you recurse on the left side. Otherwise, it's larger than the root node, so you recurse on the right side. So the else condition over here is that it's smaller, so you call recursively on the left child, where you search on the left child of the root. Otherwise, you search on the right child of the node of the root. Does that seem straightforward?
Yes, ma'am.
Ma'am, I didn't get if root equal to null, how can we say that the element is found? It should be
Right.
that no element is found. I mean, that element
Right.
is not.
So again, this is a design choice for how you're writing your code. This is how I typically prefer to write it. And then what you do is, so you would have value is equal to when you've called your search, and then you can have simply if value data is equal to the key that you were searching, then you found it, else you haven't found it. Now the same thing you can have in the function call itself, where when you're defining your function search, you have your function call here, and then this is you're returning node star if root equal to null, then you can return -1, or if you have all integer numbers in your code, then you can return int max or int min.
Ma'am, this is node star, so how can we return any integer?
Sorry, then you can just return a temp where the data is this. It's not showing up on screen, but you can return a temp node where data is -1, int max, int min. Okay, and then when you get the value of this back, when you get value equal to search, you'll have to check again if value data equal to -1 or max or min, then you know that no node, then printf or whatever you need to do with that, no node found. Does this make sense?
Yes, ma'am.
So one of the reasons, because either way you have to do this if condition in your main code. So one of the reasons why I choose to code it that way is because then you don't have to add this extra condition in your search. But when, if you're doing if value of data is not equal to the key that you were originally trying to find, then you know that either way the node has not been found, right? So adding this extra condition to the function, you don't need to do that. That it just, you don't need to add that. Did that make sense?
Ma'am, can you repeat the last what you said?
Yeah. So what I'm saying is, if I'm defining the function the way I had shown in the slide, let me go back to the slide and show you. So if I'm defining the function in this way, where if root equal to null or the root data equal to x, I return root. If I was not defining it this way, then I would have two conditions over here. If root equal to null, then I return a temporary node where the data is -1 or int max or int min, right?
Ma'am, in this code, if you return root and in the main, you will search for it, like whether it is equal to the key value or not. So
Right.
if it is null, then we will get segmentation fault, isn't
No,
it?
it
Because
won't be.
null arrow data is not defined.
Right. So if
Ma'am, or we could just do if root not equal to null in the
if
main
root not
function.
equal to null, yes, in the main function you could just do if value over here is not equal to null.
Yes, ma'am.
Sorry, it's
Then
not
it,
showing up on screen. Yeah, it's not showing up on screen, but yeah. So that way, basically, you don't have to add that extra temp node in the function, and then you don't have to return that. Okay, I hope that makes sense now.
yes, ma'am.
Let's go back. So this entire program is clear, right? Searching for a new node in a binary search tree.
Yes, ma'am.
Okay, great. Let's look at the next part. So how do you find a predecessor of a binary search tree? I believe you discussed the theory with Sir before. So it's simple. If what you're trying to do is, first you, let's say I have, I'm trying to find the predecessor of a value 35. Then first I have to locate it in the tree, and then I have to find its predecessor. And for this case, let's assume that we don't have the parent pointer. Okay. So if we are not able to locate it in the tree, that is, if root is equal to null, we've not been able to locate it, then you just return, because we haven't been able to find the key in the VST at all. If we have found it, then if the left subtree is not null, then the predecessor would be the rightmost child of the left subtree, right? And if a rightmost child of the left subtree does not exist, then it would be the left child itself. Now, if the left subtree is null, let's go back to looking at examples. So if you have 50, 20, again 30, 35, 15, 70, 80. Okay. So let's say we want to find the predecessor of 50. So for the predecessor of 50, the predecessor would be the rightmost child of the left subtree, which is 35, right? If we were to find the predecessor of 20, there's no rightmost child of the left subtree, so it is simply the left child. Okay. Now let's say the we are trying to find for 80. Right? We are trying to find for 80. Now the left subtree is null. So the predecessor is the ancestor until the node is the right child of its parent. So you move up. Now 70 is the right child of its parent. So this is the predecessor. Does this algorithm make sense?
Yes, ma'am.
Okay. Now let's look at the code. Okay. So what do we have here? We have that you start with the function definition, and you start with saying that you start with assigning the predecessor to null, and your current node that you're finding right now is root. If there is no root, this not root, that is root is equal to null, then you return null in the sense that there is no that the key has not been found, right? This is that case. Then you recurse over your root. If you check that is my current data equal to key? If it is not, then you check whether you need to go towards the left side or the right side. If you need to go towards the left side, then you simply do that. But if you need to go towards the right side, you remember that any time that we're going towards the right side, we need to keep a track of the ancestor, right? Over here, if the left subtree is null, then you need to keep a track of the ancestor. So what do? We set the predecessor to current. Okay, let me show you why this example. If I'm at 50 and I need to find for 80, then I'm at the root node. I know I need to go towards the right side, but I know that if I'm going towards the right side, it is possible that the node that I'm trying to find might not have a left child, right? Then I go towards 70, but I set this as the predecessor value. So my predecessor value right now is 50 and my current value is 70. Okay. Now my key is 80. So since 70 is not equal to 80, but 80 is larger than 70, I recurse towards the right side again. Now what do? I set predecessor is equal to 70, current is equal to 80. What was my key? My key was 80, right? Now these match. So I check whether 80 has a left child or not. So left child equal to null. There is no left child. So in that case, what was going to be the predecessor of my node? The ancestor, right? And I already have the pointer to my ancestor. I already know that it is predecessor, this value that I have set. Yes, tell me. Any questions?
Ma'am, if we had 65 connecting to 70 and we were finding predecessor of 65.
So in this case, let's, sorry. Okay. So my key is equal to 65. I start with the root node. So my current is equal to 50 right now, and my predecessor is equal to null. Okay. 65 is greater than 50. So we recurse towards the right side. but I set my predecessor to 50 and my current becomes 70. Now 65 is less than 70, so we go towards the left side. But my predecessor remains the same. Because if you remember the code, we are only setting the predecessor if we are going towards the right side. Otherwise, we just recurse on left.
Yes, ma'am. Got it, ma'am.
All right. So let me just complete this example. So your predecessor is still 50 and your current is equal to 65. Your key value match. You check. There is no left child. Left child is equal to null. And then what do? You set it to the predecessor. So predecessor is 50. So as we said, we need to check the answer. We need to find the ancestor where the parent, the node, the ancestor is a right child of its parent. Okay. So let's say if 65 also had some 60 and then this also had some 55. Even for 55, its predecessor would be not 60 or 65 or 70. It would be 50. Right?
Yes, ma'am.
Okay, great. So let's look at, let's skip this. Now, let's look at the other condition that I skipped. If we have 50 and we're trying to find the predecessor of this, what do we need to find? We need to find the rightmost child of its left child. Right? So it's pretty simple. You are at 50, you go to its left child, 20, and then you go to its rightmost child. That's it. So a simple function for this would be when you're trying to find the maximum of a node, maximum. So you try over here, it would be maximum of 20. Then you simply keep trying to find the rightmost child through this while condition. This makes sense? So you have 50, you go to its left child, which is 20. And then you're trying to find the maximum from here. Okay, so we had 30 and we had 35. So when we are at 20, we go to 20's right side. So this is the root right now. So root right. This becomes our current. And while the right side, sorry, 1 second. So while the right side of root is not equal to null, we keep setting root is equal to root right. Okay. You go at 20, you check its right side, it's not null. So you set root at 30, you check its right side, it is not null. So you set root at 35, you check its right side, it is null. So we know that in the subtree, which is rooted at 20, the maximum value is 35. Does that make sense?
So, ma'am, in the start, we wouldn't know whether our key has a left subtree or not. So we would start in the same way that predecessor current. And if the left subtree turns out to be not null, then we proceed for finding the maximum of left subtree.
Right, yes. So let's go back to the code. You check over here. If in your last conditions, once you found your key, so let's say our key was 50 and we wanted to find the predecessor to that. So you check if your 50 cut, it has a left side. Okay. If it does, then you set its predecessor to find maximum, which would give you the return value of 35. Otherwise, you would set it to the predecessor of the value that you have, the current predecessor that you're tracking. So if we go back to this, let's say we were trying to find it for 70, then what would you do? You would write, your predecessor would be set to 50 and you would seek out for 70. Now 70 has 65 as its predecessor, but it does not have any right child. So your get maximum would return value 65 and then you would set this. But let's assume that you didn't have any, you didn't have this connection. So since it does not have a left child, you simply set it back to 50, which is your predecessor that you have been tracking, your ancestor that you have been tracking. Does that make sense?
Yes, ma'am.
Okay, great. So we have less time, but okay, so these are some things that you should practice yourself. The 3 traversals that you have: in order, pre-order, post-order traversal. And you should practice deleting a node yourself as well. And everything that I've discussed, try writing the code for it in whatever way suits you. So I want to discuss the last year's assignment too, but we haven't had the time. So maybe we can take an extra class for just half an hour later. Would that be fine with everyone? Okay. Pavan sir, if you're here, would that be okay to take an extra class for discussing the assignment? Okay, it seems Pavan sir has stepped out. So yeah, this is, but what you should do is, I'm sure the last year's assignment been shared with you, with all of you?
No, ma'am.
No? Okay. But what you can do is, it's fairly standard. You can search for Huffman coding. Try to understand what it does. I'll give you a little background right now, and then I'll explain how we do it. So what Huffman coding does is, what you're trying to do is, you're trying to encode a message into the smallest stream possible. So let me show you. Let's say you have these characters where you have O is 11, I is 23, A is 25. These are the frequencies. 26, T is 27, and E is 40. So let's say you have a huge sentence or you have a huge corpus, and from that you get these frequencies for particular characters. Now what you want to do is, you want to represent them, but you want to represent them in the smallest way possible. Okay. So you convert it into a way. I'll just explain how, a little bit of what we do and how we do it. I'll explain it later. So what we try to do is, if you have E40, this has the maximum frequency, right? So if I'm trying to, let's say I have EAT and I'm trying to encode this. So I want a unique representation that I can encode using binary digits. And I want a unique representation, but I also want the smallest representation possible. So let's say I encoded E as 0, 1 and A as 0. Okay. And then I had to write, or actually, let's say I encoded E as 0, A as 0, 1. Okay. And T as 1. Now this would be very ambiguous, because for EAT, if I write 0, 0, 1, 1, then this can mean anything. This can mean EETT, right? And then because 0 is 1 over here, 0 is 1, and then T is 1, 1. But it can also mean E and then 0, 1 together form an A, and 1 means the T. Did that make sense?
Yes, ma'am.
Okay, so what we want is we want a unique encoding, but we also want to we want a unique encoding, and we want to make the smallest one that we can. So for E, if the frequency is 40, what makes sense is to encode it as, if we say 0, E is 0, and then for T, if it's 100, okay. So if at any point, and then let's say A is 101, okay. So if at any point I'm trying to represent EAT, this is 0, this is 100, sorry, this is 101, and this is 100. This can never be ambiguous, right? Because you know that 0 only means one thing, and then you have 101, because you don't have any other representation that starts with 1. So you don't have 10, you don't have just 1, you have 101, or you have 100. So you know that this can only mean A, and then you know that this can only mean T. Okay. Did this make sense? Now,
Yes.
yeah. Now, why do we try to encode it in this way? We use 0, 100, 101, and what the logic is behind the code that we have. This I'll explain next time. And if you want, then you can read up a little on it. I'll explain the method that is there, and we can discuss the code also for this in detail. So we'll try to have the extra class tomorrow. You have that. Okay. So I'll try to find a time and then I'll get back to you. And if you have any other question regarding the codes that I've shared today, any other part, then you can just ping me and we can chat. Okay.
Ma'am, do these PDF are being shared with us?
Yes, this PDF will be shared with you. I'll just share them.
Okay, ma'am.
So all of this code all of the code walkthroughs that are there, I'll share them with you. Okay. Any other question? You can also, I've also listed 3 more problems over here, which is kth smallest element in BST, and is binary tree a BST, and merging 2 BST. So I've defined the problem, and you can also go through the codes for the algorithms for this and then try to code them yourself. Okay. I haven't added the code to this, but I've written the algorithm, and then if you face any problem in coding it, you can ping me. Any other questions? Otherwise, we'll break. Okay, I guess that's it. So we'll end this call now.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.